Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 16th lecture. In this lecture, we will be continuing with logic optimization. In the earlier lectures, we had looked into combinational logic optimization, and in today's lecture, we will be looking at sequential logic optimization. Now, sequential logic optimization works on the FSM representation of a given circuit. So, let us first understand what is an FSM. FSM is an abstract mathematical model to represent a wide variety of sequential circuits and many other systems. For example, biological systems and many other systems also use FSM for its modeling. Now, what does an FSM consist of? An FSM consists of a finite non-empty set of states, and that is why it is known as finite state machine. And an FSM also has a finite non-empty set of inputs and outputs, and we are given that among the set of states, what is the starting state from where the FSM started. And an FSM also consists of a state transition function. And what does the state transition function describe? It describes that given a current state and the input, what will be the next state. So, that description is provided by the state transition table or state transition function. Now, how is the output modeled in an FSM? Now, output can be modeled in two ways in an FSM. The first way is that the output depends only on the current state. If that is the case, then we say that the FSM is a Moore machine. And the second case is that the output is a function of the current state as well as the current input, right. Then if the output depends on both these things, then we say that the FSM is a Mealy machine. Now, how do we represent an FSM? One of the convenient way to represent an FSM is using state diagram. And what is a state diagram? State diagram is a directed graph. It is a directed graph in which we annotate, we have vertices which represents the states. So, in a state diagram, the state corresponds to the vertices in the graph, and what does the edge corresponds to? The edge corresponds to the transition from one state to the another state, and the edge starts from the current state and it goes to the next state. And at the edge, we annotate that what input made this transition from the current state to the next state, right. For example, suppose we have a current state as state 1, right, and the next state is state 2 when the input is input 1, then we can represent it in this form. Now, how is the output modeled? Now, output is modeled by either marking the output at the vertex. For example, if this is a Moore machine, so the output depends only on the current vertex or current state, right, and therefore, we can mark output directly at the state or the vertex, right. Now, for a Mealy machine, the output depends not only on the current state, but also on the input. So, in that case, we mark the output on the edge. On the edge, we say that given a state and the input, what will be the output produced and what will be the next state, right. So, now let us look into an example, a very simple example to understand what is a FSM. So, let us consider a regulator of a fan, right. Now it can be described as an FSM, and we suppose that in this fan regulator there were 4 settings. We just label them as S0, S1, S2 and S3. These are 4 settings, and these we consider them as states. S0 state S1 state, S2 state and S3 state. And we say that the initial state is S0. For example, we start with the state S0. Now, input to the fan regulator is either we rotate it clockwise or anti-clockwise. So, there are the input set contains two elements, clockwise movement or anti-clockwise movement. And suppose we say that at state 0 the speed is 0, right, and that is the output, and at state 1 the speed is 1, state 2 speed is 2 and state 3 speed is speed 3, right. So, we define the output at each of the states. And what are the transitions from one state to another? So, when we rotate say clockwise, then we move from S0 to S1, that is from one setting to the next setting, then from S1 to again to S2 to the next state or next setting of the speed, and then to the third, and again if we rotate clockwise then we again reach S0, right. So, this is clockwise movement. Similarly, there will be a rotate anti-clockwise, right. So, whenever from a given state if we rotate anti-clockwise, we go from say from S0 to S3, then S2, then S1 and then again reach S0. So, these are the state transitions that is described, that is defined for a fan regulator. Now, how can we represent this in terms of state diagram? Let us look into that. So, this is a very simple representation of the FSM for the fan regulator. We have four set of states S0, S1, S2 and S3, right. And if we rotate clockwise, we go to S1, if we rotate again clockwise, we go to S2, clockwise S3, clockwise again reached S0, right. And similarly, we go anti-clockwise like this, right. And on each vertices, we mark that what is the corresponding output S0. For the S0, we have the output as speed 0. For S1, we have the speed 1, for S2, we have speed 2 and S3, we have speed 3. So, these are the outputs. So, this is the finite representation of the FSM of a fan regulator as a state transition graph, right. Now, which kind of FSM is this? Is it a Moore machine or a Mealy machine? Now, since the output depends only on the current state, we can say that it is a Moore machine. Okay. So, now having understood what an FSM is, now let us look into that how actually FSM can be implemented in a circuit, right, how we can implement an given FSM in a circuit. So, FSM is implemented using flip flops and combinational circuit elements. So, this is a representation of an FSM as it will be implemented in a sequential circuit. So, we represent the states by the combination of Q pin value of the flip flops. So, we will have the flip flops and the output of the flip flops. So, this big chunk represents a set of flip flops and the output of them of this set of flip flops are denoted as Q, right. Now, this output of this flip flop will represent the state of the or the current state of the FSM, and there is a transition function is implemented using a combinational logic CL, right. Now, what this transition function is doing is that given the current state and given the current input, what will be the next state? What will be the next state? And that is going to the D input of the flip flop, meaning that whenever the clock will come at the next clock edge, the next state will be reached and so on, right. And also the output is being produced by this combinational logic element, right. So, now how to this will be like the way in which an FSM will be implemented in our circuit. Now, what kind of optimizations can we do in this circuit, right? So, we can optimize, there are two things we can optimize. The first is this flip flop set of flip flops, and second is this combinational logic which implements the next state function and the output function. right. So, the first thing of first optimization, that is optimization of the state elements or the flip flops, that is done using a technique which is known as state minimization, right. So, when we minimize the number of states in an FSM, then we will be reducing the number of flip flops required in this implementation and we can save area. And the other thing is that if we choose or find a good encoding of the states, what we mean by encoding we will just see, we choose a good encoding of our states, then we can optimize or improve the combinational logic, we can improve the combinational logic which is required to implement the next state function and the output function. So, let us look into both this technique, the state minimization technique and the state encoding, how we can optimize by doing state minimization and choosing a good state encoding the FSM implementation, and therefore, the sequential circuit representation will improve or the area will reduce. So, what is the motivation of doing state minimization? Why do we want to minimize a state in our circuit? So, to represent an FSM, we use a sequence of bits. For example, suppose there were 3 states S1, S2 and S3. Now, how do we represent this? We represent it using sequence of bits. In this, we can choose a represent, we can say that we represent S1 as 0 0, S2 as 0 1 and S3 as 1 1. Right. So, we represent each state as a sequence of bits, and for ns states, ns is the number of states, for a given number of states, how many bits do we minimum require? So, the minimum number of bits will be required will be log ns to the base 2 and then we take the ceiling of it, right. For in this case there were 3 states. So, the number of bits, the minimum number of bits required for this case will be 2, right, it will be 2, right. It will be, say, log 2 to the base 2 is equal to 1 and log 4 to the base 2 is equal to 2. So, this log 3 to the base 2 will be something between 1 and 2, and if we take the ceiling it will turn out to be 2, right. So, if if the number of states and the number of bits required are related, right. So, by reducing the number of states, we can reduce the number of bits required in an FSM representation, right. For example, if we are say 100 states, if and we reduce it to say 50 states, right, then the number of bits required for the representation will reduce and therefore, we can save in the number of flip flops and area. Why? Because the flip flops are used to represent the state bits. For each bit, for example, in this case there are 2 state bits 0 0. So, for each of them we will have one flip flop that represent each state bits. So, if we reduce the number of states, we will be reducing the number of bits required to represent a state, and if we reduce the number of bits required to represent a state, then we will be able to reduce the number of flip flops required for an FSM, right. So, that is the motivation of state minimization. We want to reduce the number of flip flops in our circuit. So, what is the objective of state minimization? The objective is to derive an FSM that has the minimum number of states and exhibits the same behavior as the original FSM. So, we have got an FSM in which there are certain number of states, we want to minimize it, reduce it, and such that the new FSM that we are getting is functionally equivalent or is functionally same as the original FSM, right. And to do state minimization, what we rely on is we rely on determining equivalent states. Now, what is an equivalent state? we consider two states, suppose there are two states S1 and S2, we consider them to be equivalent if these two conditions are fulfilled. The first is that they produce identical outputs for the same inputs. If we give same input to both these states should produce identical output. And the second thing is that the corresponding next states are the same or equivalent, meaning that there are two states. Now, if we give same input to these two states, then the next state should be the same or should be an equivalent state. If these two conditions are satisfied, then we say that the two states are equivalent. And when we find that two states are equivalent, then what we can do is that we can retain any one of the equivalent states and remove others, and then we update the transition function to maintain the same behavior as the original FSM. So, let us take an example to understand this. Now, consider this FSM which is shown here. There are three states here, SA, SB and SC, and there are two inputs A and B and two outputs 0 and 1, right. Now, let us consider whether the states SA and SC are equivalent or not. So, let us examine whether they are equivalent or not. Now, first let us look at the output for the state SA and SB. Now, at the output for the state SA, if we give the input as A, then the output is 1, and for the states SC, if we give an input as A, the output is again 1. So, that is same, right. So, when input is A, both states produce 1, and when the input is B, this produces a 0 and the state SC also produces a 0, right. So, when input is B, both states produce 0, and let us look at the next state. When input is A, and the current state is SA, then it goes to SC, and SC is considered, we are considering SA and SC as equivalent. So, it is going to an equivalent to a state SC, right. And if we take the if we consider the current state as SC and we give an input as A, then it goes to SA. Now, SA and SC are equivalent. So, when we are giving input is when input is A, SA transition to SC, which is considered, and SC transitions to SA, and we are considering SA and SC to be equivalent. So, they are transitioning basically to the equivalent state for the input A. What about when the input is B? If the input is B, then SA is going to SB and SC is also going to SB, right. So, both SA and SC are transitioning to SB, and therefore, they are transitioning to the same state, and therefore, the next state condition is also satisfied, and therefore, these two states are equivalent, right. Now, if these two states are found to be equivalent, what we can do is that we can retain one of the states. Say, let us assume that we retain SA and we can remove SC, and we can get this kind of FSM, right. So, for the case A is equal to 1, whenever input is A, then it is going to the same state, right. So, this extra edge is created, and SC is eliminated. So, we could have as well retained SC and eliminated SA. The behavior of the FSM would remain the same. So, there are efficient algorithms, polynomial time algorithms, which can be used to find equivalent set of states for a given FSM, and those algorithms are used to find for state minimization in the logic synthesis, right. Now, let us look into the other problem of an FSM, that is state encoding. Now, what is state encoding? State encoding basically assigns a binary representation to each state of an FSM. For example, let us consider again a 3 states S0, S1, S2. There are 3 states. We can assign it as S0 as 0 0, S1 as 0 1, and this one as 1 1. We could have as well assigned this as 0 1, this as 1 1, and this one as 0 1 0 0, right. So, we can assign binary representation to each state in many different ways, right. Now, the problem of state encoding is that how should we assign it, such that our FSM implementation is optimal, right. So, how does the state encoding impact the behavior or the area of our circuit? So, changing the state encoding can change the next state function and the output function. So, next state function and the output function can change as we change the, for example, this encoding and this encoding are different, and for these two different encodings this function CL will be different, and one of them will be actually giving us a more compact combinational logic CL compared to the other. So, combinational circuit block CL and the associated QR can change with encoding. So, that is what the motivation is for the trying out various or looking at various encoding scheme and finding a good implementation or good encoding for our FSM. Now, we can also consider the encoding length of our FSM representation. For example, if we consider say the state 3 states S0, S1, S2, we could have represented, for example, as I said 0 1, 0 0 0, 0 1 and 1 1. This is one of the encoding scheme. So, what we have seen that if the number of state is ns, then we need at least log 2 ns and the ceiling of that many number of bits, right, minimum. That is the, for a n states we require log n to the base 2 and the ceiling of that many number of bits in the FSM implementation or in FSM encoding. But we can always go more than that, right. We can always choose a longer encoding length than what this minimum is. For example, for the 3 case, the minimum turns out to be 2, that is we need to have at least 2 bits for the 3 states, right. But we can also choose a longer encoding, or the encoding length can be longer. For example, we could say that we do a 1 hot encoding. So, in 1 hot encoding we reserve 1 bit for one state. So, in this there are 3 states. So, there are 3 bits we will be using. For example, we will use 0 0 1 for the state 1, sorry, state 0, 0 1 0 for state 1 and 1 0 0 for state 2. So, we are reserving bit, the lowest, this bit for this state, this bit for this state and this bit for this state, right. So, this kind of encoding scheme is known as 1 hot encoding, right. So, 1 hot encoding reserves 1 bit for each state, right. Now, why will we want to change the encoding length? Why not always the minimum? So, there are complicated dependencies on the encoding length and the number of flip flops and the input output of the logic block CL, right. So, of course, when we increase the number of bits, then the number of flip flops will increase, but what effect it will have on the combinational logic, that is not very easy or straightforward to think in terms of the figures of merit. For example, the area and also the timing. For example, sometimes combinational logic block can be simplified by changing the encoding length. For example, one hot encoding identifies a state, or if instead of say minimal bit, which was say this is minimum, right, this encoding scheme is minimum and this encoding scheme is 1 hot, right. Now, in one hot encoding, if you want to identify that what is the current state, we can just look at one of the bit and find out, right. And the identifying whether we are in a current state or not is very easy in one hot encoding scheme. In contrast, if you want to identify the state, which state we are in in other kinds of encoding scheme, for example, in this encoding scheme, we have to look at 2 bits and take the corresponding say min term, and then based on that min term, we can say that we are in the current in a given state. For example, if we denote this in this encoding scheme, we denote the first bit as A and this as B, then the min term which will identify the state S0 will be A bar B bar, right. And therefore, the identifying whether we are in the current state will require more logic in other encoding scheme than in one hot encoding scheme. And as a result, what can happen is that the one hot encoding scheme can have fewer logic levels between flip flops and be faster in some cases, right. And therefore, we can try with different encoding length also to optimize our FSM. Now, given an encoding length, how to find or choose a good encoding scheme, right. So, there are challenges is that the number of possibilities is huge, right. Say if there are 50 states and there are say 50 state bits, then there will be lots of possibilities, exponential number of possibilities in which we can assign or encode states with 50 bits, right. So, now brute force cannot be of course applied in these cases to examine all the possibilities and come up with a solution, right. So, and the other challenge with this is that though we have discussed first the combinational logic optimization and then sequential logic optimization, and we have done this because it is easy to understand sequential logic optimization after understanding say combinational logic optimization, but in practice sequential optimization, logic optimization is typically done before the combinational logic optimization. So, when we are actually doing sequential optimization, sequential logic optimization, at that stage the combinational logic which implements the next state function and the output function, that is not yet implemented, right. So, we cannot easily assess the effect of an encoding scheme on the QOR or the figures of merit of the combinational logic block, right. So, we have to choose an encoding scheme, or we have choose an encoding scheme in FSM optimization such that in future when combinational logic optimization is done for the block CL, that is combinational logic block that is implementing the next state function and the output function, that gets optimized, right. So, during FSM optimization and choosing an encoding scheme, we must encode it such that in future when this logic block CL is optimized, that optimizer sees lots of possibilities of optimizing and makes this CL as compact as possible. So, what does the tool do, or how tools approach this problem? So, the CL needs to produce the next state function and the output function. So, this combinational logic is being used by next state function as well as output function, and therefore, it is the same logic elements or circuit elements will be used in multiple outputs, right, multiple functions. It will be implementing many different next state function and many output functions, and therefore, the same CL logic block is used for implementing different logic functions, right. So, we can do the encoding of the states such that the sharing of this logic element inside this CL element is maximized. If that happens, a lot of sharing happens, then this CL can be very compact. And so, we should choose an encoding scheme that allows more common cubes and common sub expressions sharing among the various logic elements. If we are able to do that successfully, then our encoding scheme will yield an FSM which is compact or having a good figure of merit. So, what tools do? They follow some heuristics algorithm. They define what is known as gain, which somehow quantifies the possibility of common cube extraction or common sub-expression extraction for a given encoding scheme, right. So, given an encoding scheme, it tries to formulate it, or it tries to formulate an expression or function called gain, which somehow captures that how much sharing of logic can happen in the element CL for a given encoding scheme. And then it tries to determine an encoding scheme that maximizes this scheme, right. So, at a broad level, at very broad level, this is what the tools will do while finding a good encoding scheme, right. Now, if you want to go deeper into these topics, I will suggest that please go through these references which are shown in these slides. And just to summarize what we have done in today's lectures, we have looked into sequential logic optimization, and we have in particular looked into an FSM representation of a sequential circuit and how it can be optimized using state minimization and state encoding. And also let me summarize what we have done in last 3 lectures. In last 3 lectures, we have looked into logic optimization of a net list consisting of generic logic gates. Now, given an RTL, we did RTL synthesis and we also did logic optimization. Now, while doing these transformations in our RTL representation, was all this transformation correct in terms of functionality? So, we have initially, when we have written an RTL, we have done a say functional verification using simulation and other methods, and we have verified that the initial RTL is correct, functionally correct. Now, once we have done these transformations, that is RTL synthesis and logic optimization, are we still sure that the functionality remains the same? We have to actually make that or we need to ensure it that the logic optimization and RTL synthesis task that was performed, that didn't ensure any that did not introduce any errors. So, we have to somehow ensure the equivalence of the initial RTL and the netlist that we have after say RTL synthesis and logic optimization. So, this kind of equivalence between these two models can be established using technique which is known as equivalence checking, and these equivalence checking is done using formal methods. So, in the next lecture, we will be looking at various formal verification techniques. Thank you very much.